See you later.
So just a real quick introduction, Nikki, to everybody. April just joined us 2 days ago.
Hello.
She's covering the Midwest, Mid-Atlantic kind of region. Johann is out of our German office, and he's the business unit manager for the German office.
Pleasure, John.
Hi.
You know Alan?
Alan, yes,
Yes.
Ashley. I think everybody else I'm
Ashley,
on
you know
a
Ashley?
name-by-face basis.
And Jean, the one that
Jones.
just stepped out, right, covers the
That's
West.
very well.
Okay, welcome.
Thank you, appreciate it. I'll just set my stuff right here. Hope you all got a lot of good information today, so as we move forward, I'm actually here on Dr. Shuiji Zhang's behalf because he would have been giving this, but he's out of the country, so he has over 20 years in research and testing on all our sensors. So if there's anything I don't
Speak up,
cover,
you gotta speak up.
if there's anything I do not cover, or you can't get the answer to, I'll be sure to make sure that it gets forwarded to the appropriate person. So, moving along. Go slow here. Okay. What are our sensors designed for? What are their benefits to using our sensors, to using the TBR system that we have? Obviously, we have a lot of different aspects, a lot of different benefits. The TBR 4100 has 4 different ranges for detection, for measuring current. You can also auto-select your species of interest, setting your poise voltage, which is automatically predetermined by how it's set in the system. You have a wide measurement bandwidth for all your data. There is an analog output for each channel, and you also have an integrated temperature channel. So, because of the design, you can measure 4 different species at one time with an appropriate setup. You could have one channel set for oxygen measurement, one channel set for hydrogen peroxide measurement, and so on. These are our macro scale 2mm sensors. The columns are designed for the species measured on the left. Our WPI part number is in the middle, and the detection ranges are on the far right. I have here in the case, which we pass around, some of you are probably familiar with it, the 2mm sensors are on the far right to color code as we have described at the bottom. The carbon monoxide has the orange color code, hydrogen peroxide has yellow, oxygen has green, and the isonop is white. One thing that I don't have on here, the isonop sensor, we can customize this detection limit to go higher. That's a custom pricing, so if customers want that, we can certainly do that for them. And just call for a request for a concentration and custom price for that.
For the hydrogen?
For the nitric oxide, the isonop. It can go higher than 80 micromolar if necessary. It is in the catalog, I think asterisk for that. Moving along. These are our microscale sensors. This page is specifically nitric oxide. We offer a lot of different nitric oxide sensors, different lengths, different diameters. The left column is your diameter going from smallest diameter, which is a 100 nanometer tip, all the way down to a 500 micromolar. I'll pass this around if anybody would like to see. The 100 nanometer, 7 micron, and 30 micron, they are not flexible fibers, very delicate tips. Your 100 micron and higher are all flexible. Some of them, like the 200, are available in an L-shaped configuration.
Why?
An L-shaped configuration. There's one in the case. When I say L-shaped configuration, the body of the structure of the sensor is in an L shape, but the tip comes out flat. Yes, that's right up here. So you can see this is just the body structure being the L shape, but the tip still comes out as a straight tip. The tip itself is not bent.
Excuse me,
Yes,
can I
ma'am.
just ask one top question, right?
Sure.
So, we have these sensors.
Yes.
Where do we use these sensors? Where are they pushing these sensors into? What are they doing with them?
The people that will use our sensors are tailored to veterinary science, research institutions, the biomedical field. People that are doing research wanting to measure nitric oxide, hydrogen peroxide in muscle tissue, in vessels, in cell cultures. So target markets would be veterinary science, veterinary research, institutional research, biomedical engineering, biomedical fields. Those are the types of people that'll be using our sensors.
So I could have a tissue slice
Correct.
or a whole part,
Yeah.
for example,
Yeah.
or a cell,
Exactly.
and I'm going to put this probe into the
Cell culture,
cell
tissue,
culture or the
tissue.
tissue, and I'm going to make this measurement.
microvessels.
Are these sensors using up the oxygen?
All the sensors behave just like a battery would. They're not, indeterminate, forever shelf life. As you use the sensor, it's going to deteriorate in terms of performance over time. So when you say is oxygen being consumed,
Yeah.
what happens, yes, at the surface, you're actually seeing a degradation in the reference and counter electrode performance because of the oxygen reacting. So that's what happens to the sensor itself. So, which leads me into another question about shelf life and how long the sensor can actually use for a customer, which I'll get into at the end of
Because there's an essential difference between the optical oxygen sensors where it was stated it is not consuming any of the
Correct.
oxygen in the environment, which will influence the testing itself.
Right, because obviously when it's optical, you're not, using
Yeah.
per se the materials of the sensor itself.
This is more like active muscle or something like that. Where
Correct.
It's not, yeah.
Right, correct. The next slide indicates all of our other 100 micron diameter sensors. These measure different species and they're also built a little differently. The previous slide, all the nitric oxide microsensors, they all have a carbon fiber element to fabricate the performance of the sensor. All of these use platinum wire as the sensing element. The glucose sensor has a coil-shaped design. This is to hold a membrane-infused piece of cotton for this to function properly. The hydrogen peroxide sensor.
Sorry,
Yeah,
I
go
don't
ahead.
understand. So why is it coil shaped? What's so important about that?
Well, the glucose sensor, in order to behave and detect the concentrations it can and to last, as long as it can, the platinum wire has to be shaped in a coil so that it can be infused with a membrane enzyme on a piece of cotton. Once.
So I'm going to take a piece of cotton.
No, it's already built like that.
Oh,
You don't have to do anything with it. You can use it as is. It's just the fabrication of the design.
It's just the enzyme which
It's
is
a enzyme
the
reservoir.
factor.
It's an enzyme reservoir.
okay.
Yep.
It's the one sensor that's different and that's enzymatic. Once you wet it, it starts to work,
It starts to
whereas all
work.
the other ones are more solid state.
So once you dip it, it's only one-time use. The glucose one.
Yeah.
Well, I mean, yeah, like if you're going to use it in vivo and this is on a manual, you're going to get about 2 to 3 weeks of use out of it. If it's
Okay.
continuous use because of the application. The hydrogen peroxide sensor, we manufacture this in a couple of different ways. The HPO 100 and the H sensor, these come out as a straight tip. The H is for a hypodermic needle, which can be used for implantation. The HPO 100 can also be designed as an L shape, as you saw in the previous slide, where again the body is fabricated in an L shape with the tip coming out straight. And the hydrogen sulfide sensor, which is one of our, I think, recently popular sensors. A lot of people are ordering this.
Is the L shape used for exposing extra surface?
Usually,
Did you lay it down on a layer of cells or something like
yeah,
that?
usually the L-shaped sensor is for use in a tissue bath. There's a schematic in the catalog for people wanting to have that specific application where they want to enter either from the side instead of directly down. So, again, one big difference between the 2mm sensors and all our microsensors is that you have to have a separate cable to attach our sensors to either one of the units. And in this slide, graphically, both the 1025 on the left and TBR 4100 on the right, they behave, exactly the same. It looks a little bit different on the face, but there's a temperature and sensor analog output on the 1025. There are 4 for the 4 channels on the 4100, and all the current ranges, are preset. All your poise voltages are preset. There is a custom adjust if the customer wants to use one of our sensors.
Could you maybe explain what the working of poise voltage is as it relates to the sensor itself?
Correct, yeah. Good question, Perry. All of the predetermined poise voltages for the sensors will dictate the way all of our specs are reported. So, as an example, for nitric oxide, the voltage that's applied is about 860 millivolts, plus or minus a couple. If it differentiates wildly from that value, all the numbers and specs are going to be vastly different. So that's something very important with the design of the system, that if it is radically different from what it's supposed to be set, it's going to create a lot of variance in the data reported.
Will it actually be detecting different species other than the one you're looking at if you're off from the normal poise voltage?
No, it won't detect different species. It's just going to have different values for your baseline current when you're recording, data. So the only thing that's going to come into effect is concentration, where you will have a different potentially effect if you're trying to measure super high concentrations with our sensors.
Linearity will be increased.
No, linearity won't be affected. Linearity, all the sensors behave in a linear fashion. I mean, at least greater than 90%.
And if you have now, for instance, water peroxide with the 200 micromolar, how will impact that on well, say, because it's only 200 micromolar. If you then have 200 micromolar, can it still be accurate?
Yeah, well, if it's depending on the sensor, like if you have a nitric oxide, the 2 millimeter sensor is designed to measure optimally 80 micromolar and higher.
Mm-hmm.
All of our sensors are designed to measure accurately low concentrations. So if you try to measure high concentrations with our
So
sensors,
it's not working, or you should ask for, can you dilute the sample or whatever?
yeah, you should ask for, try to get a lower concentration, because obviously if you want to measure high concentrations of substances, you can go titrate it, easier than you'd be using our sensors. That's not what they're designed for. One of the benefits, and what's what makes us unique from everybody else, is the fact that we're able to routinely detect nanomolar concentrations of substances. And I believe, Perry, I think Ziad is one of maybe the competitors that also sells sensors, but they don't have anywhere near the detection limits that we offer on ours. And that's,
So this client wants to have a TBR 1025 and says, I have 200 micromolar of HCO2 peroxide. He's measuring then with a pencil what you normally would do with a shovel or something.
yeah. Well, again, with the application, no,
I mean, I like to sell it. I mean,
yeah, of course. No, as I said, that
but I need to be able to promise him.
Yeah, you have to explain that. Well, what concentration are you looking at?
Yeah,
and then
he told me. So.
Right. So if you're looking at 200 micromolar concentration of hydrogen peroxide, then I would, the first thing I would say
use
is
the macro. First, I would use the macro.
Use the 2 milliliter HPO2 sensor,
Yeah.
and then the other thing is that what we report with all our ranges, we ensure you're going to have linearity in the ranges we specify. It does not mean you can't detect higher than that, but then you start to see ineffective linearity.
You don't want to treat it.
Yeah. So that's why we report that as such.
So I'm sorry, I have to go back to poise select. So I've got this
Mhm.
probe, right, and I'm hooked up to the tissue, right?
Okay.
And now I'm gonna hook it up to the TBR 4100. What am I going to adjust with this poise select?
The poise select is based on just whatever sensor you have.
Yeah.
So one of the reasons that our sensors are color coded for the 2
Oh, it
millimeter
says
size.
that, okay.
Yeah, it's very small,
I got
but
it.
yeah.
So all I do is just select whatever
Correct.
sensor I have, I just select.
Yeah, they're just nomically like NOs for nitric oxide,
Okay, got it.
H2S is
Okay,
hydrogen
got it. I
sulfide.
got it.
Doesn't it have to do with the redox potential? So it's, a chemical detection component.
Right.
It has to do with the redox of the chemical.
So the software adjusts for that,
Right.
once you select it.
Correct, once you put the knob in the right position.
Right. And there
Automatically
is, yeah,
selects.
and then,
that drags up.
yeah, of course, there is, as I mentioned, an adjust knob so that the customer can choose a completely different voltage if they want.
I know it says this, but the question is, customers can ask you, what is this for?
Mhm.
What are you going to say? This is just selecting, I thought it was poise select, sorry.
No, well, yeah.
It was probe select, I got it.
It's probe select, but-
Forget it.
No, but one good thing that I haven't mentioned yet on here, the switch is nominally in the down position for output current, but when you flip this up to applied voltage, you can go through and verify, as the instrument is supposed to be, that nitric oxide is supposed to be 860 on this display, hydrogen sulfide is supposed to be 150 on this display, just like it is in the manual manufacturer.
And when are you changing the under range?
Yeah, the range can be based, one, on the application, and two, on the type of sensor that we have. A lot of times, people are testing at 37C to mimic, human blood
Mhm.
condition. So because of that, a lot of times people will be operating in this 100 nanoamp range. If they're measuring current, they can certainly measure in voltage or any other type of units they choose to.
So if you misselect, it's not giving a problem.
No, only thing that will be a display on your data acquisition system where your units will change based on it. That if you're in the 1 microamp, range, for as an example, you may see on the display 0.015. So you know that if you switch that to 100 nanoamps, it's going to be 0.15 on the display. You just
Okay.
factor a 10. So you just have to work on
So
the
it's,
units.
so it's not really, it's only the scale.
Correct.
It's always measuring the same, but you want to see it in a resolution that you can really see it.
Correct. Yeah, based on the responsiveness. Next slide. Here is a typical scale and plot of our ISONOP 2 millimeter nitric oxide sensor. On the left here, you can see that these linear plots are, very smooth, very minimal noise. And another big factor is response time, that people want to know that they're measuring in real time, that they're not waiting on some sort of part of the sample. So these are always within less than 10 seconds. Some are less than 5 seconds for response time. And what is happening on the curve here is at this point where you see this slope before it starts to plateau, this is the part where the sensor is detecting the nitric oxide and it's generating a response, which is this plateau of the curve, and then this is the part where it starts to reach its maximum potential, and then the nitric oxide starts to decay rapidly, which we are able to catch. Then the same thing with the next plot. If you double the concentration, the curve doubles in height, hence the linearity of the sensor. And we go through with 5 different points here, and as you can see, the linearity very well over 99%. And we have this plotted as currents versus concentration in nanomolar range. And the next slide I will show you is also a nitric oxide sensor. This is our flexible 100 micron nitric oxide. And again, a little bit noisier than the previous slide, but this also, the same concept, when you have an injection and you have nitric oxide that is being produced, you see this rise in current. And then when it starts to decompose or it starts to come down, you double the concentration, the height of the curve doubles. And again over here, you can see that this obviously is a much more sensitive version of 2 millimeter ISONOP, so we have a larger value here. So obviously somebody wanting to detect very low nanomolar concentrations, this would be the sensor to choose as opposed to 2 millimeter ISONOP, because you can see if you need to measure really low concentrations, this is going to get you the sensitivity you want.
Is concentration on the y-axis then?
Concentration is down here on the x-axis. Again, it's a small, if you blow up the print screen, you would see here labeled the aliquots, and current is on your y here. Concentration is on the bottom here.
Is there a recording of time in there?
Yeah, where's time?
How do you-
Yeah, the time is, this is data track software, so you can take 2 cursors and the time will be reported up here at the
So
top.
he's right, it's time across the bottom, but
Time's
between
across
the
the bottom,
lines, he's
correct.
doubling the concentration between the lines. So you really got a concentration and across the timeline change, if that makes sense to you. So every time it jumps up, he's doubling the concentration, but he's doing this, maybe every 10 seconds, so he's kind of spaced it out. So it is a time scale across the X.
The whole time scale is probably 2 to 3 minutes
Right.
for all 5 points, because nitric oxide rapidly decomposes within seconds. So you're going to go right away to do the next point in the calibration.
Yeah, think of that as a chart recorder tracing, not a actual graph.
Right, yeah.
So it's basically
Time.
those dots are supposed to be right there. So it's not supposed to be these lines. You're supposed to just draw this line. Is that what you're?
Which one?
Look, you
the-
have
the-
time
the-
this way and you have current this way.
Yeah.
And then he's correlating the current component in the y-axis here with the concentration he knows.
So the x-axis here is time?
Is
Right.
time, correct.
That's a chart recorder tracing, that's not a graph,
Okay,
actually.
okay,
That's- The
that
graph
makes
is the
sense. Okay.
concentration.
That's,
Yeah.
that's time
It
versus.
could be,
Okay.
yeah, it's, yeah,
It's time.
it's
Okay.
time.
The vertical lines you're looking at over here are the insertion of the aliquot points. They are not the high and low points for each aliquot. That's something you're not seeing here. There are many, many steps to get to that calibration data.
The little thin line, you can, is that the where he's taking the?
You can't quite see it.
These black lines are just marks to indicate when I actually made the
The next
aliquot.
one.
Right.
The data acquisition software usually has a 5 to 7 second delay between the time that it records and displays the data.
So you see a difference in slope and there you say, okay, I'll set it here.
Yeah, roughly. And these can be edited in the software for lab tracks. You can, if you mismarked it, you can
What's
go back and edit.
LabTrax? That's a great
So,
Well, oh yeah,
WPI.
lab track is just a
What is
data
that?
acquisition software that we sell with our TBR systems.
Yeah, you need to register because otherwise you don't see anything.
Yeah, really.
Yeah, well,
Yeah, it's just, that's what we record all our data with, our sensors. Customers can use a different data acquisition system and still use our sensors, that's not a problem. What is one concern, people will, from time to time, use our sensors on some other analyzer system, and they could also use, our analyzer on somebody else's sensors.
but that's,
And one of the things we do on our packaging, and we make this note that before they open the box of the sensors, there's a label there that our sensors are designed for use with our systems. We do not guarantee performance on anybody else's systems. So that's also very important to keep in mind.
So the key thing of this WPI technology, right, there are very few others that can really do this. We have the world-leading recognized person that does this. It's Rick. He's world
Don't talk
renowned,
about
many
this.
folks.
Yeah.
we don't talk about that.
I imagine you can do it on a standard potentiometer, but it's much more difficult. This is much more of a user-friendly way. Instead of having to, set knobs to 865 millivolts and.
Yeah, to go in and adjust it, yeah, potential.
So it's a way to collect that data,
Right.
right,
Right.
and say that.
But now you only
This is
have
the
the
key,
measurement,
in real
where you only
time.
have the scale.
So it's not
Now
at
you
one
get to
point,
the
it's in
point
real
where you
time.
have a sample which you don't know exactly what's in it.
Right, and this is the thing that we always tell people, that when they get our sensors, when they get our sensors, the first thing they should do is verify our calibration, so they have an understanding of what the sensor does. Then they can go ahead with their experiment and accurately measure, their samples.
Does it need heating time or do you need to, before you do the calibration, do you need to put it in, soak it in
The-
solution or?
All our sensors have pre-set polarization times
Okay.
for stability. For the F100, it's usually a few hours. For the 2mm ISONOP sensor, it's 8 to 12 hours. So,
It takes 8 to 12 hours for it to
Peroxide?
stabilize, and then I can take a measurement?
correct.
And for peroxide?
calibrate it.
Yeah,
And you can calibrate it, right?
hydrogen peroxide is usually a couple of hours. The
Okay,
HPO 100.
so you need to go, for a demo, you need to go in the morning, early
You
8,
better
to
book
the
it.
client,
You
and
better
then
book it.
after
Well,
lunch, you
Well,
come back.
but if you're in discussion with the client, you can say, hey, I'm going to be in tomorrow. Make sure you have the sensor polarized overnight. When I come in tomorrow, we'll do it
I
first
don't want
thing.
them to do all the measurements before me arriving.
Oh no, it's just polarizing. That's it. Oh, that's all we're
Yeah, I
doing.
mean, you know.
Paper
the-
Disconnect it. On that,
Polarizing is just connecting it?
yeah, it's just connecting it. Yeah, so
Yeah, just
and,
connecting it, putting it on, and
yeah, letting it go. So yeah, the next slide.
Why?
This-
Because you're thermally stabilizing the sensor? Why do you need to turn it on?
Well, it's just like anything else. You have to have the analyzer on so that it applies that voltage continuously over a period of time to stabilize it. If it's off, it's just like cutting the power off to anything else. That's not going to be ready. Alan?
So why does it take that long? Like, what are
Um,
all these influences that's making it not stable?
Well,
Never heard of any-
part of it's the fabrication of the sensor, that with the materials involved, again, what we're doing is we're actually applying a voltage, and just like a battery. You have a half reactions going like this. So it takes sometimes several hours for the item to stabilize, so that you get that current flow exactly.
buffers in the sleeve, and yeah.
Correct, right. Just quickly, so I wanted to show here, this is a 2mm hydrogen peroxide sensor. And again, linear measurement, similar graph. But I want to point out on this, you see has concentration of micromolar on the 2 millimeter. When we go to the 100 micron, this is nanomolar concentration. So they both measure hydrogen peroxide, but one is vastly different concentration than the other, which goes to, if you're trying to advise somebody, hey, what is your, what are you trying to measure? Well, what's your concentration? Well, if they want to measure micromolar concentration, this sensor is not going to work well for them because it's designed to measure nanomolar concentration. So you'd want to give them 2 millimeter version as opposed to the 1 millimeter version. Or 100 micrometer, sorry.
What's the relationship, surface area to concentration range? More surface area, more concentration? So
Generally,
basically bigger is
yeah.
higher?
Yeah, if you double the surface area, as an example, if you have a 2 millimeter length tip as opposed to a 4 millimeter length tip, your 4 millimeter is going to roughly behave double the response to sensitivity. So
We don't have.
we don't have 4, but all the tip lengths of the small sensors, that they can be ordered with custom lengths. If I go back
Okay,
here,
so if I have a client who says, I want to have a measurement of maximum 200 micromolar, he can order, but then it's a customized version.
well, I'm saying, yeah, a 3 millimeter length tip, a 4 millimeter length tip, yeah.
Like it.
Yeah, well, I said, well, people will have different, like, they're in a well plate, or they're in a,
What's the delivery time there?
Generally speaking,
I mean, there was an issue with that or not?
if we don't have items in stock,
Yeah.
from the time it's cut from the sales order, it's usually 2 weeks. A lot of times it's less than that, but especially if it has to be custom. So here, go back here. Oh, want to make sure everybody's still paying attention, so I put that slide there.
Another question, why is temperature always included? Temperature in the measurement, what's the relationship between concentration of hydrogen peroxide
Oh.
and the temperature?
The concentration is not affected by temperature. What affects your plot, temperature and current is sensitive to that. So if you're elevated at 37 C, your baseline current is going to be higher than what it is at room temperature.
The basic kinetics of molecules or something?
It just has to do with, if you have an expansion in temperature, you're going to have an expansion in material and
It's the density of the material itself.
correct. So that's something that is important. Also, that people should calibrate the sensor at the same conditions they're going to run their experiment. If they're going to test at 37 C, they need exactly. That's something good. These are questions that I would be asking a customer if I was out, in the field. I would be asking, first and foremost, what is your application? Well, are you working in cell culture? Are you working in a tissue bag? That's going to help you funnel, what type of sensor they should have. Because if we give them a sensor that doesn't fit their application, then nobody benefits at all. I mean, because then we got to take it back and, then as a second, major point is, will follow, well, what concentrations are you going to work with? Because again, as I made an example with the hydrogen peroxide, you can measure in micromolar or nanomolar concentration. It makes a big difference. And again, it's not going to help your application if you need a high version. There's another, this third one is something that I come into contact with sales orders, is that people a lot of times will get grant money and then they want to buy our stuff and they have no intention of using it for 8 months or a year.
Yeah.
So one of the things that I always like to tell everybody coming in contact with here is that we can always provide sensors down the road. If they want to buy it, but they have no intention of using it for 6 months, let us know that, because
Okay.
yeah, I mean,
No, this is it, take the order.
yeah.
Don't you buy it later. Let me help you out, take the order, we can deliver later.
Yeah.
Take the order.
Sensor is like a carton of milk. It will go bad.
Yeah.
Order your milk.
And I know you would ask earlier, this first question that customers would ask you, how long will the sensor work for? Like for me, if I purchase this, is it going to last a day? Is it going to last
Yeah,
a
but
week?
it's also depending on how long they use it. I mean,
Yeah.
if they use it 24 hours for 7 weeks, it
Right.
will be broken.
Right. Yeah, I mean, we nominally warranty everything for 30 days on everything. That you'll at least get 30 days of continuous use out of it. Now, with the example, the 2 millimeter sensor, it has a consumable sleeve. If you change the sleeve once a month like you're supposed to, you probably get several months, possibly even like 1 to 2 years out of the sensor, if you do that.
That's
The,
also the one you use for demos, because the other ones is way too sensitive.
Yeah, the,
I will just ask them to order it.
yeah, the microsensors you're looking at probably, 3 to 6 months. If you remove protein aggregate off of it when you're testing, you gotta do all those things because and then the last one I had here are like how should I sort of the sensor not in use that, again, it's in the manuals, but that's important if you're gonna be using it for several months. And the last one is, kind of a, can I use the sensor in
Magma.
exactly X, Y, Z? You always get those questions.
But
A
Yeah.
common,
you
a
can
common
only
there.
guarantee, if I'm correct, you can only guarantee the calibration. Everything else the client has to do himself, because otherwise
Right.
you are
I say
the method.
another easy response is, I'm sure there is research out there on that, and then you can always
You
come
can
back to
help,
me
yeah.
and say, hey, is there any research paper out there on, because our sensors have been in use over 20 years. There's tons of research papers out there, and I believe,
scholar.
I sent earlier, I think a larger PowerPoint, more extensive than this, that Alec had done, which has research
So
papers
we
and
can,
covers.
we'll roll that one into your disc.
Yeah.
We don't print out everything, just.
Oh, you got
so
that
you
one.
have
Who gave it to you?
I think.
Well,
Did I give it to you?
Well, yeah, because you were doing it for Keyshen years ago.
That's right, yeah.
And so yeah.
So before you, can you go back to that one?
Sure.
Do we have a process to clean?
Yeah, it's in the manuals.
It's in the manual?
Yeah,
Okay.
because one of the things with our sensors, like again, if they're using it in a protein-rich solution, as an example, they need to be able to remove that off the tip if they're gonna continually test. If they don't do that, it's gonna muffle the readings and, it's not gonna work properly. So, we sell, I think, what do we sell, Rapicide or something, I think?
Well, that's like an enzymatic detergent.
Yeah, but I'm just.
Oh,
yeah,
that'll be
that's-
perfect. Just wait till this afternoon. You'll hear all about this, the detergents we're gonna
Right.
release.
Yeah, so, and
Rapicide
then,
is a sterilant.
yeah. That's important. So again, summary, it talks on this, analog outputs, simultaneous temperature measurement, accessories for everything.
Okay.
That's all I have.
One
Hang on.
questions?
Go ahead.
I just had one questions that
Yes, sir.
came through. As nitric oxide has a very short half-life to begin with, and is consumed by oxygen, people will ask, can I use this in blood? How do you respond to that?
Well, you can use it in blood depending on the type of concentration and, the type of response time you're looking at, because, the oxygen's not gonna interfere with the concentration of nitric oxide if the concentration of nitric oxide is low enough, because oxygen we're measuring in percentage, which is not nearly as accurate as substance as measuring a nanomolar concentration of nitric oxide. So,
So if they want to elicit a response of the endothelial cells to see if they can change nitric oxide response, is it at that level that can they measure that?
at that level with appropriate sensor, yes, they can. If they're able to have, like I said, measuring nanomolar concentration of substances, that's one of our, highlights. But not everybody, they can make an oxygen sensor, but can you detect this
Like
concentration?
we're making oxygen sensors that
What I
Rob
could-
spoke about, right?
Oh,
This
what
in
is
a
this
totally
Speaking of
different
consumption, they do
level.
consume, because they are electrochemical sensors.
Sure. Yeah, it's just the fact that, again, if you're, the concentration of your analytes, that's the.
So there is no competition? There's,
Well, as I mentioned to Perry, Ziod's the only one I know of. They manufacture
Yeah, small
sensors.
company though.
And you got the spin tramp also.
There's a company out of the UK as well. I can't remember the name of it. They just sent you an email about that today,
Yeah.
actually.
Yeah, I can't remember the name of it right offhand. There are a few.
They
few
make
competitors out there.
macro sensors.
but
in there.
everybody, if you say this kind of measurements, everybody knows, oh, Billy's guy.
Pretty much. Yeah, I mean, you type in like isonop on Google, there'll be all kinds of papers.
I think you have a
Just-
fluorescence technique, and then you have an external technique. None of them are real
Grease.
time. That's the selling point here, is that it's real time.
Real time.
Within 5 to 10 seconds, right?
Mhm, mhm.
Okay, so it's pop quiz time.
Oh, gosh.
Okay. So what types of biosensors do we offer? To measure what?
Your next page?
No.
Oh.
I'm tomorrow.
Are you?
Thank you very much, Nikki.
Can I see the picture again?
No, we can't see any picture. Nikki spoke. What kind of biosensors do we offer? When you go into, when you